Section: Introduction. In this section, we will discuss the impressive abilities of large language models, LLMs, in various tasks, such as generating coherent text and understanding language. These models are powered by the transformer architecture, which uses self-attention and feed-forward layers to combine information efficiently. Despite efforts to understand how these models work, they still remain somewhat mysterious. By gaining a better understanding of how transformer layers function and how they are influenced by training, we can develop new techniques to monitor and improve these models. Predicting the next word in a sentence involves different challenges. For example, if the context is, John gave a book to, predicting the as the next word is straightforward based on common patterns. However, if another character like Mary is introduced, predicting Mary requires more complex reasoning. Previous research suggests that attention heads in the model are responsible for such in-context predictions, while feed-forward layers focus on broader statistics like common word pairs or general knowledge. Recent studies have shown that replacing certain layer weights with simpler versions can enhance performance on reasoning tasks. By studying how these mechanisms develop during training, we can see how global associations, like common word pairs, are localized in specific parts of the model. Our research delves into pre-trained language models like Pythia to understand these processes better. We also explore simpler models to investigate how noise in data affects learning. By analyzing the dynamics of these models, we can see how global associations and in-context reasoning are learned and separated within the model. Removing specific components can lead to improved predictions on reasoning tasks. Other studies have observed that simplifying certain weights in pre-trained LLMs can boost reasoning abilities. Different research has looked at the roles of attention and feed-forward layers in various tasks. Feed-forward layers are crucial for storing general knowledge, while attention heads are essential for complex reasoning tasks. In the next section, we will provide background information on reasoning tasks and rank reduction, along with our initial findings on pre-trained language models. Section Summary. In this section, we delve into the capabilities of large language models, LLMs, powered by the transformer architecture, which excels in combining information from input context using self-attention and feed-forward layers. By studying how transformer layers are influenced during training, we aim to unravel how global associations like big RAMs are localized within specific components or layers of the model weights, potentially leading to enhanced performance on reasoning tasks. Our investigation on pre-trained language models and simpler data models reveals that noise in predictions is predominantly learned in feed-forward layers, and low-rank truncation can effectively filter out noise, shedding light on how in-context reasoning mechanisms are acquired and distributed within the model. Section: Layer Selective Rank Reduction. In this section, we empirically explore how large language models, LLMs, handle associations within context versus global associations, and how this changes during training. We focus on two models, GPT-2 Small and Pythia, and examine their performance on tasks involving indirect object identification, IOI, and factual recall. For the IOI task with GPT-2 Small, we investigate if the model predicts words beyond the given input. For example, when given the input, when Mary and John went to a store, John gave a drink to, the model predicts Mary correctly as the indirect object target. However, it also suggests them and the, which are not even mentioned in the context. This tendency to predict such generic words aligns with our earlier findings and may stem from a global association mechanism based on the context. By applying laser on specific layers of GPT-2 Small, we observe a decrease in the probability of predicting these extra words, indicating an enhancement in contextual task performance. Moving on to Pythia 1b, we extend our investigation to multiple models and track their behavior throughout training. By conducting IOI experiments on Pythia models of varying sizes, we observe that laser on MLP weights significantly increases the likelihood of predicting the correct indirect object over generic words like the. Similarly, in the factual recall task, Laser improves the model's ability to provide accurate answers based on context rather than generic responses. Analyzing the training dynamics of Pythia models on IOI and factual recall tasks reveals distinct phases. Initially, the model struggled to differentiate between different tokens, but gradually learned to prioritize contextually relevant information over generic associations. The training process highlights that the models tend to grasp global associations earlier than complex reasoning, possibly due to the simpler grammar structure required for generic predictions compared to the intricate attention mechanisms needed for contextual understanding. Our experiments lead to several key observations. Firstly, global associations can hinder ILM's performance on reasoning tasks. Secondly, applying laser on MLP weights in LLMs can help mitigate the influence of global associations, thereby enhancing in-context predictions. And finally, during pre-training, models tend to learn global associations before mastering complex reasoning tasks. These findings prompt further exploration into why global associations are learned earlier and the role of feed-forward layers in this learning process. Section Summary. In this section, we propose the Layer Selective Rank Reduction (LASER) method, which involves reducing the rank of MLP matrices in specific layers of large language models, LLMs, to enhance performance on reasoning tasks. By applying laser to weight matrices of MLPs in deeper layers with an optimal rho value below 0.2, we observed improved model predictions by shifting from generic words to context-based answers. Laser helps inhibit global associations in LLMs, leading to better in-context predictions, and during pre-training, we found that global associations are learned earlier than complex reasoning, prompting further investigation into this phenomenon. Section: Two-layer transformer on noisy in-context recall. In this section, we explore two-layer transformers in the context of an in-context recall task with added global noise. This setup allows us to investigate important properties we observed earlier in a controlled environment. We demonstrate through experiments how transformers tackle this task by storing the noise in feed-forward layers, while attention handles the in-context mechanism. Additionally, we present theoretical insights showing why feed-forward layers are more inclined to retain the global noise association, based on the analysis of gradients during initialization. Our data model is similar to the one previously discussed but with the inclusion of extra noise. We define a vocabulary set containing tokens from 1 to n, with an additional token n plus 1 representing noise. We select a trigger token q within the range of 1 to n, which controls the in-context recall, along with a context length t. Each token sequence z1, t is generated by first sampling a correct output token y uniformly from 1 to n. Then, we sample z1, t1 based on a specific Markov process, where z1 follows a distribution pi_u and zt is set as the trigger token q. The final output y is sampled based on a distribution p_alpha, y, where alpha is a parameter controlling the noise level. In our study, predicting the correct output y involves reasoning based on the context, while also learning to associate the global noise triggered by alpha, similar to the bigram case discussed earlier. We also explore the use of multiple trigger tokens in our analysis. Moving on to the two-layer transformer architecture, we consider a simplified version with input token sequence z1, t and output xi. The model includes fixed embedding and unembedding matrices, learnable attention and feed-forward layers, and cross-entropy loss for predicting the final token y. In our experiments, we utilize character-level distributions from the tiny Shakespeare dataset to estimate pi_u and pi_b, with model parameters set to d equals 256 and two-layer MLPs with ReLU activation for the feed-forward layers. During training, we use a batch size of 512 and a context length of 256. When evaluating the trained models, we focus on the impact of noise level alpha on the model's performance. Our experimental results indicate that the full model predicts noise with a probability close to alpha, as expected from training. However, when removing the second layer MLPF2, the model shows a significantly higher accuracy in predicting the correct output y. This suggests that F2 plays a crucial role in storing the global trigger noise association. We also observe that the model initially prioritizes predicting noise before focusing on the correct output Y, similar to the dynamics seen in learning the to-the bigram. This highlights the relative ease of learning the global trigger noise association compared to predicting Y. Furthermore, we notice a gradual learning process of an induction head mechanism after mastering the global noise association. This mechanism, represented by the second layer attention head, filters out noise tokens and attends primarily to non-noisy output tokens related to the correct Y. Our exploration into this mechanism is detailed in the following sections. Section Summary. In this section, we explore the behavior of two-layer transformers in an in-context recall task with added global noise. We demonstrate how transformers handle this task by storing noise in feed-forward layers and implementing the in-context mechanism through attention. Additionally, we provide theoretical insights into why feed-forward layers are more likely to retain global noise associations, as evidenced by studying gradients at initialization. Section: Theoretical Analysis. How and why do feed-forward layers store the noise? In this section, we observed in a figure that our model quickly learns to predict the noise token after a few steps. The gap between ρ equals 0 and 1 in the figure indicates that the feed-forward layer F_2 is responsible for storing the overall association related to noise, as confirmed in another figure. We will now explain the theoretical reasoning behind this behavior. The model we used in our experiments is quite complex, involving various components and nonlinear MLPs, making it challenging to fully understand its dynamics. Therefore, we simplify our focus to a model with a linear feed-forward layer and an attention layer to analyze the gradient dynamics near initialization. We find that the gradients related to the feed-forward parameters carry more valuable information compared to the attention gradient, which is mostly influenced by noise unless the sample size is very large. This highlights the feed-forward layer's capability to capture the global association effectively. Let's consider the input x_t in math bbr (d) at position t, defined as x_t equals w_e z_t, where z_t in n+1 represents the token at position t and w_e c_dot gives its embedding. For simplicity, we omit positional encoding at the beginning since it does not provide much information during initialization but can be included later. In our model, given a sequence of inputs x_1 t in math bbr (t times d), the output is she equals she_text attn plus she_text ff, where w_u in math bbr (n+1) times d is the unembedding matrix phi s t, represents the attention module with query s and context t, and f c_dot is a linear feed-forward layer. This architecture resembles a single-layer transformer and already emphasizes the distinction between feed-forward and attention layers, which we believe holds true for multiple layers as well. In this parameterization, the trainable matrices are w_kq, w_f, and w_v in math bbr (d times d). Initially, we set w_kq, w_f, and w_v to 0, assuming that random initialization in high dimensions would lead to similar behaviors due to near orthogonality. We then examine the first gradient step from initialization, commonly used to comprehend feature learning and sample complexity in neural networks. The theorem we present discusses the resulting logits for the feed-forward and attention blocks after one gradient step, providing concentration bounds on the impact of updates on w_f and w_v on predicting the noise token. Our analysis reveals that during the initial training phase, feed-forward layers are more likely to identify the noise token, while attention layers may progress slower due to additional noise and potentially smaller step sizes. This suggests that attention layers may focus on learning the induction head mechanism instead. Exploring this balance further would involve studying the dynamics of other attention parameters, such as key query matrices, which we leave for future investigation. Section Summary. In this section, we explore why feed-forward layers store noise in neural networks. By analyzing a simplified model with a linear feed-forward layer and an attention layer, we find that the gradients over the feed-forward parameters are more informative than those over the attention parameters, indicating that feed-forward layers are more likely to capture global associations, especially in the initial training phase. This suggests that attention layers may focus on learning other mechanisms, such as induction heads, due to additional noise and smaller step sizes. Section. Theoretical Insight. Attention avoids attending to noise tokens. In this section, we gained insight into how attention in our model helps to avoid focusing on noisy tokens. When the feed-forward weight learns to predict noise, our findings show that the second layer attention in the model directs its focus only towards the correct tokens. On the other hand, a model pre-trained without noise initially attends to all tokens after the triggers, as seen in the attention pattern in the first step. However, after fine-tuning on noise data, the attention shifts to concentrate solely on the correct tokens. To understand this mechanism better, we need to analyze the behavior of the W_KQ matrix. By simplifying the model and data distribution, we move closer to understanding how attention steers clear of noise tokens, as explained in the appendix. Specifically, this mechanism arises because, after the initial training phase, W_V has a structure that projects less onto W_U, n+1, W_E, n+1, top, causing W_KQ to adjust towards W_E, n+1, W_EQ, top. Further exploration of the dynamics of W_KQ during training could be a promising avenue for future research. Moving on to linear associative memory, we demonstrated that fully truncating a feed-forward layer can aid in reasoning tasks. We introduce a scenario where noisy associations are stored in a rank 1 subspace of a layer, making intermediate levels of truncation more effective in eliminating noise. In our model and data setup, we focus on a simple associative memory task where the objective is to learn a fixed permutation from input tokens to output tokens. We utilize a linear model with a learnable weight matrix, W, and embeddings for input and output tokens. We introduce a common noise output token selected with a certain probability for any input. During training, the dataset includes noise, while at test time, the dataset is noise-free, leading to a pure label loss computation. Our experiments involve training the model using gradient descent on cross-entropy loss. The results are presented in the figures, with detailed discussions provided in the appendix. We observe that the rank 1 subspace corresponding to the smallest non-zero singular value stores the noise, as proven in our analysis. Furthermore, we discuss the limitations of our study and propose future research directions. We aim to delve into more complex data models to understand how transformer language models handle global associations compared to in-context inputs. Exploring the training dynamics and behaviors in architectures where global associations are stored differently, such as in attention mechanisms, presents an intriguing avenue for further investigation. Additionally, a detailed examination of the training dynamics of SGD across different matrices and phases could provide valuable insights for future studies. Section Summary. In this section, we gain theoretical insight into how attention mechanisms in two-layer models avoid attending to noise tokens by learning to predict noise during training. By analyzing the dynamics of the weight matrices involved, particularly W_KQ, we uncover how attention focuses only on correct tokens after being fine-tuned on noise data. Additionally, we demonstrate that fully truncating a feed-forward layer can aid in reasoning tasks, especially in settings where noisy associations are stored in a rank 1 subspace of a layer, making intermediate levels of truncation effective in removing noise. Section. Acknowledgements. In this section, we express our gratitude to Yifang Chen, Ekin Okurek, and Denny Wu for their valuable discussions.